All right, Newton's method. Have a calculator handy for Newton's method, and if I can remember, I'll add to the screen here what I do whenever I use Newton's method on my calculator so that you can see it. You can do this with both the 84 and the Nspire, this little trick. But basically, it's just like a division algorithm. You're just going to take the same process and go through and through and through it. When you get to the end and you get a number, that's the number you're going to start with for the next time through the process. So let's just real quick have some sort of thing of what Newton's looks like, and it looks like this, where the next term, n plus 1, all right, is equal to our original term minus the function at that term divided by the derivative at that term. And basically, this is a really cool way to find zeros. And you just need to be in the ballpark of the zero that you're interested in. And once you're in the ballpark, after a few times through Newton's method, it lines everything up exactly perfect, and you can get a zero to like 7 or 8 decimal places, which for us is really pretty good. A lot of times when we are trying to find a zero, we're only interested in maybe 3 or 4. So the problem they give us here is 2x to the 4th minus 3x squared minus 7x plus 1. We're going to need a derivative in there. So here's your derivative. And then what we're going to do is we have to pick a starting zero. And there's 2 zeros on this particular problem. And the first zero looks like it's close to 0. The second zero, and you'll need to graph this to looks like it's close to 2. Okay? So what I need is, I need the function at 0, which is 1. I need the derivative at 0, which is negative 7. And so here's what I punch into my calculator. x1 is equal to 0 minus 1 divided by negative 7. And I did that on my calculator, and I got 0.142857. All right, now for the second derivative, or the second term through Newton, we're going to take this number 14287 minus, and then we're going to do the function of that. And what you want to do is you want to keep that original number in the function because you want as many decimal places as you can get, divided by the derivative of that. And when I punched that into my calculator, I got 0.135148. And then I'm going to come down here for the third guy, and we want it to be accurate to 7 decimal places. So we want to be able to line these decimal places up so that they're the exact same. All right. So the third guy, 0.135148 minus the function of that divided by the derivative at that. And this gets me 0.135 12698. And I'm going to do that same process again. And I'm kind of running out of room, so I'm not going to write out exactly what it is. But you see the pattern here. And so when I work this pattern with 0.135 when I get done, I end up with 0.135 126,985. And notice how these guys match all the way to here. Notice how they match all the way to there. So that's when we know that we've gone far enough, when we can line up all those decimal places together. So I'm going to do the same exact steps over here on part 2. So I need to know f of 2, and I need to know f prime of 2. And once I've got those things, I use these steps, and I punch everything into my calculator, and on my calculator kind of grind through some stuff. Um, so I need to know what these two guys are, and what I got. I punched all this into my calculator. You can too, and I'll show it. But for x1, I got 1.8444. For x2, I got 1.8123. 9368. For x3, I got 1.8111. 03994. For x4, I got 1.1811. 0195. 2. And then when I did the second one, or the fifth one, I got the same thing. It changed back here, but I'm not worried about that. I just want to line up those. So I'll have a calculator up that shows you how to do this also. It's really easy to do. It's just an algorithm. But that's how Newton's method works. It helps you find zeros of graphs. And you don't necessarily need to have a graphing calculator to do it, although a calculator sure came in handy.